Thanks. Thanks for the introduction, and thanks to the organizers for the invitation to this really interesting workshop. What I will be presenting is, first of all, can you hear me well?
Very well.
Okay, I have some echo, but yeah, if you can hear me, it's fine. So this is joint work with Andrzej Murawski, who's at Warwick, and actually I believe Andrzej was here in the previous workshop about a month ago, and myself. So what I will be talking about is some recent work we did on linearisability. So what is linearisability? It's a correctness criterion for programs, like or libraries, if you like, in the context of programming languages. And in particular, libraries that you can assume that, we assume that they are called concurrently. So many clients or many threads may be calling a library. And then if you look at the behavior of your program or your library, then it gets more involved because of all these different threads and how they communicate and how actually they affect, for example, the common state that the library may have. And in particular, the criterion is used, one use is to show that a specific piece of code that you wrote adheres to a specification that you would like. And in general, this theory is applicable to first-order programs. I will say what that means, but it basically means you have libraries where, for example, do computations from integers to integers. Like that's what I mean by first-order. And what Andrzej and I did is we took some ideas that we already knew from game semantics and applied in this setting in order to extend this notion to higher-order programs. Okay. I'll start with some picture of the setting. So I will assume now we have. So this is code. Well, I mean, it's an abstraction. So this L is a library, and this case is a client, and the client has some programs, some methods that they run in parallel, M1 to Mn. And when they run, they use some methods from the library, but the methods have type theta. So this theta is a set that says, for example, if my library is a queue, theta will have two methods, enqueue, which goes from int to void, which means I give you an integer and you enqueue it, or dequeue. So I call dequeue and I get back the end of the queue. Right. So that's the interaction. Okay. And now we want to look at the thread, like the traces or the histories, if you like, that we can produce by this simple scenario. So we have enqueue and dequeue. So let's see. Here is a diagram of what behaviors we can have. So time goes from left to right. Yep. And then here I have threads. So this is one thread, the second thread, and the third thread. And at the beginning, we have the first thread calls enqueue, and it wants to enqueue 1, the value 1. And the library returns and says, OK, I enqueued it. And then the second thread says, OK, now I want to enqueue 2, and then the library returns. And then the third thread, when it calls dequeue, and since this is a queue, we would like what the client returns to be 1, because 1 is the first thing in the queue. Okay? Now we can see this is a very simple setting because there is a clear distinction of where things start and end between different threads. But I can make it more complicated. I can say, OK, suppose that while this is enqueuing, another call to enqueue has been issued. And this is still a legal behavior because, OK, the two enqueues happen concurrently. So it may be that this one finishes first. So therefore, when we dequeue, we get that back. And actually, it could even be like that these things happen concurrently. And although this one returns first, it actually is the case that this one was enqueued first. It's just that the return action was delayed to come out. But it's indeed this guy who was enqueued first. And therefore, when we dequeue, you get back that. And I can make it even like that. I can say, oh, well, even if I call this first and this second, it may very well be that this guy is enqueued first, so when I dequeue, I get 1 back. Okay? What I shouldn't be able to say is that I call enqueue of 2, this returns. I call enqueue of 1, this returns, but then when I dequeue, I get 1. Because here there is this clear distinction that, okay, this guy finished, and then this one was called. So it better be that 2 was enqueued first. So we see that some behaviors we allow, some behaviors we don't allow, or we wouldn't like to allow. And this is what the criterion I'm going to be introducing next is supposed to capture. So the criterion is called linearisability, and it says, well, a behavior is correct if it follows a given specification that I have. So the specification I would have for a queue would be if you enqueue and then you dequeue, well, you should dequeue always the top of the first element in the queue. But you can, so a behavior is correct if it follows a given specification modulo some reorderings of actions. And the reorderings have to do with internal delays that you have when the library computes. And this notion has been introduced in the 90s, in this paper, and by now it's a standard criterion for concurrent programs. So if I went back here, I had this behavior at the beginning, and we can see that this is sequential in a sense, so things happen in sequence. There's no concurrency. When this finishes, then the next call is afterwards, and then they're separated. So I can say, okay, this is a correct specification, and now, excuse me, this is also correct because if I swap these two events, I arrive here, and I know that this is correct. Okay, so I start from this specification, and I want to check its correctness and say, I can assume that these things can be, I can swap them because they happen concurrently. So it may be that this one finishes before this one is called, and therefore this one is correct. Or if I have this situation, I can say, okay, maybe I can exchange these two, and I know that this is correct because I can exchange again and reach a valid specification. But here, there's no reordering I can make reasonably, because if I reorder these two events, I start from something that was sequential, and I impose it to be concurrent. Okay. So we would say that, so suppose now we have what I was describing before. I would like to make it a bit more formal. So we have a setting of histories of observable actions, and actions where these calls and returns I was having in the diagrams. And I will say, I say that actions A and B can be transposed if they appear in different threads, and they're not of the form a return followed by a call. So in a sense, they're not sequential. It's not that we can distinguish that something returned and something else was called. If not, that is not the case, that I'm allowed to transpose them. And we say that a history H1 linearized to H2 if we can get from H1 to H2 by using these transpositions. Okay. So what I was showing before was legal transpositions I could do in histories. Okay. And then if I have a library, then I can say that the library linearizes some specification if every history in the library can linearize to another history that is inside the specification. And the specification is given in set of sequential histories where I have a call followed by return, I have a call followed by return. And we can see why why we want to write our specifications like that. We want to do this because these are sequential histories, and we can reason more easily about it. So to go back to my example, I had this, and when I show you, I said, okay, it's obvious that this is correct because, well, it's a sequential program in a sense. So this is good as a specification. And then I use this as in order to judge whether other histories are legal. Okay. Okay. And And then when I was talking about legal transpositions, I was maybe a bit vague. I mean, maybe there is some intuition that I was able to pass to you, but actually this can be made very precise. We can say that a library L linearizes to another library L prime, which means every history in one can be linearized to a history in another. We can prove that if this happens, then this is a sound criterion in the sense that L is an approximation of L prime observationally. And this was showed in this paper quite recently. Observational approximation means that if I put any client K and I link it with L, then this composed program terminates to some value. If it terminates to some value, then this composed program here would terminate with the same value. Actually, here I don't even need to say the value. Just if it terminates is enough. So in a sense, the client cannot have more behaviors here, cannot observe more behaviors in L than in L prime. And that's what makes the reasoning sound. Okay? Now, I want to extend this to higher order libraries. And now the setting becomes a bit more complicated. So we'll have a library here, L, and I will have a client again. And now the library provides these methods, theta prime. So remember, these are method names, and I also have their types. But it also depends on some other methods, theta, for the ones for which it doesn't have the implementation. And it uses a third library, a parameter library, where this parameter library provides implementation for these methods here. So there are three players, if you like, here, and they exchange actions between them. The client is the one who starts the computation by these terms here, and the client can also directly contact the parameter library possibly by this other method, theta double prime. So what we would like to do is to look into the interactions we have here and come up with a notion of linearisability that generalizes the previous notion and is also sound. Okay? So, and actually this is something that has been examined before, but only for the first order case, so where all the methods are from int to int. In the higher order case, we have methods that receive other methods as inputs and can produce other methods as outputs. But the first order case was done by these people, and actually quite recently, which is and that work instigated actually our work. Okay. So to show why this setting is more complicated or more elaborate, I will have this. I will demonstrate this higher order queue, where the enqueue, we enqueue methods. So you enqueue methods of type int, arrow, int, and when you dequeue, you get back integers. And now the trick is the following: you give a method, you enqueue it. You give another method, you enqueue it. And you have your little queue of methods. And then when you ask to dequeue, you dequeue the first method, and you apply a number to it. And this number comes from a counter that you keep internally. So for example, if I enqueue M1, and then I enqueue M2, and then I call dequeue, then the dequeue will call, say, M1. The counter is 1. And when M1 returns, I will return what M1 returned. If I was called to dequeue again, I would call M2 with value 2, and so on. Is this clear? So why I'm presenting this? Because now, if you remember before, we had calls and returns, and the client was calling, the library was returning, and that was all. But now I have more complicated, I have added more behaviors, which was, at this point, the client calls, and the library calls again. So it calls back to the client. So in terms of game semantics, well, what we have here is a game between two players, the client and the library. And they exchange these actions or these moves between them. So in particular, when the client wants to dequeue, I take the method that I have in my queue, but the method comes from the client. And in order to find out what the value is for one, I have to call back to the client. And not only that, I can make it even more complicated. I can say, well, I enqueue M1 and M2, and then when I'm called to DQ, I call M1 with 1. So now it's the client. I'm calling back to the client. And the client says, well, in order to return, I will call back and call DQ again. And then the library says, okay, I'll take then what I have in my queue, which is M2, and apply 2 to it. And this is called back to the client, and the client would reply. So the game gets more complicated. So in general, what happens is I have these calls issued by the client, and the client gives methods as inputs. And then the library can call back these methods. So it gets a bit more elaborate than before. So in particular, a method call will not be followed by its return, because I have a call followed by another call. And everybody can issue calls and returns, the client, the library, and also the parameter library that I didn't include in the previous examples. And not only that, but before, when I was calling and returning, the methods were given in the type, in the interface. I had enqueue and DQ. Now I have all these other methods that appear out of, well, not out of thin air, but appear during the interaction, and they can be called and returned again. And when you see this at first, it may look very difficult to reason about this. But actually, this is exactly what the theory of game semantics for program does for you. This exchange of moves is exactly what game semantics models. Incidentally, in this setting, it's not even clear what sequential histories are. Before, sequential histories were calls followed by returns. But here, if we take this approach, it would be very restricted, because in some scenarios, there's no way you can get a call followed by its return. So this is a one-slide presentation of game semantics. So it's more propaganda rather than me explaining it very properly. But it's a theory where we actually explain higher-order programs in a way that is both operational and denotational. In particular, when you have a program, you model its computation as a two-player game between the program, which is the proponent of the game, or P, and an opponent, which is the environment where the program sits inside. So the environment calls your function, the program computes internally, and it may return, so produce a return move, or it may need to call a function of the environment, so it will call back. And this exchange of calls and returns is called moves, and the interactions, the formal interactions, are the plays of the game. And programs are modeled as strategies for the player that models a program. And this has a very nice denotation presentation. You can compose strategies, and you can define categories of games, and then starting from simple ingredients, model whole programming languages. In particular, this goes back to the 90s and the work of Samson and Rad and Pasquale. But and since, I mean, and also so it started from like languages like PCF and idealized algo, and in recent years it has moved to languages like ML or Java. What you achieve with game is that you have this denotational model, but it also has, because of you have plays, you also have intentional information, and the level of intentionality you have is optimal in the sense that you can show that you don't have any extra information in it. And this you can show by full abstraction, saying that the behaviors I have in my model are exactly those that are observable. And in this work, actually, we use an approach where you present the model completely operationally, using traces and trace semantics for open programs. But it's equivalent to the traditional game semantics presentation. Okay. So going back to my scenario, I have L, the library L, and then I want to link it in this setting. So say, well, I'll take L. I compose it with L prime, and then I link this composition to this client here. And then I will model this as a game where the proponent is the library, and the opponent is the combination of these two guys. Okay. So to give you very quickly what the syntax is, it doesn't really matter. We could have used the same setting for different syntax, but we needed some syntax to prove our theorems eventually. So we have libraries, and the libraries have methods, abstract and public, and then you define your methods, and then you say, here are the definitions of my methods. So a method M has this body. I also have references. I can say the reference R has this value initially, or this value. And then the method bodies will come from a functional language with references in this case. And then clients are just compositions of terms. And then the types that I have in this language are just simply the simple types of unit integers and using products as well. Okay. And now a history. Suppose I have theta and theta prime, which are sets of methods with types. So a history is a sequence of pairs like this, where T is a thread identifier and A is an action. So the action is either a call or a return of a method, M, and V is some value that comes from the previous syntax. And down here, I also have an index X, which says which player played this, either opponent or proponent. And I have some conditions which histories I allow. For example, for each thread Ti, calls and returns have to be well matched. When you return to the last method that was called, and it hasn't been answered yet. And the two players alternate, for example. And I also have some conditions that say if you want to call a method, it better be introduced first. So it might appear either in the types or somebody played before you. And obviously, P cannot call its own methods, only the methods that the other player introduce and so forth. And these are just conditions that allow me to formulate when a play is well formed. Like there is a possibility that the scenario a scenario like the previous one can produce it. Okay.
These are really just the standard game semantics things, but they match.
Yes, so it's like standard game semantics, but the pointer structure has been replaced by method names. So it's like a concrete nominal representation of games. It's interesting because, it's also interesting because this is very operational, but it makes sense to people that have worked on operational methods. Whereas the pointer structure maybe is more denotational. Okay, so going back to our examples, I had this queue with NQ and DQ. I had like this interaction, and now the history corresponding to this one is there is a call to NQ in the first thread. There's a call to NQ in the second thread. This then return, and then there is a call of DQ in the third thread, and this returns. And then I had this other example with the higher order queue. And now what I have is I enqueue a method on thread 1, I enqueue a method on thread 2, and this return. And then there is a dequeue on thread 3, and this then issues a call on M1. M1 returns, and the dequeue returns the same value. Okay. And I can make this even more complicated and include so this was the library goes from theta to theta prime. Previously, theta was empty, but I can say, okay, there is a parameter library here that provides me a full method that goes from void to int. And then what I want to say is I enqueue twice, and when I want to dequeue, I call this extra function, and this gives me a value. And now I call the method that I have in my queue with this value. So I make this. So in this case, this method, this call and return, is issued to the parameter library. Okay. Okay. And now I want to define the linearisability in this context, and the criterion is quite simple to formulate. So I will say that these two actions can be transposed if and only if you of the following form. They're on different threads, T and T prime, and this guy here is an O action, so it belongs to opponent. So if this happens, then I can say that the opponent actually answered later. And dually, I can transpose this to if this action on the right is a P. It's a P action. It can go on the left. I mean, these look like equivalent, but obviously here, this also applies if you have OO, and this applies if you have PP. And then the definition is as before. I say that H1 linearized to H2 if we can get from H1 to H2 by these transpositions. And also, what does it mean for a library to linearize to a specification, where if every history in the library can be linearized to a history in the specification. And almost as a byproduct, we also get a definition of what does it mean for a history to be sequential. Well, it's just those histories where every opponent move is, or opponent action is followed by a P action on the same thread. So before it was a call followed by return, now it was an opponent action by a P action, because obviously P can be answered by calling again. Okay? So this is the definition we introduced. Let's see how this works. So this is the relation, is PO. The way I read this is that it means that P moves can always move to the left, and O moves can always move to the right. So if this was the initial example we had with the first order Q. So we had this, and I can say, okay, this move here, it's a P move. So according to this mnemonic, it can be moved to the left. So I can move it there, and I get this one, and I can see that this one is correct because it's sequential history. So I NQ1, I NQ2, and then I DQ1. So then I say, okay, this history is correct. But then I had this other history, which I said it wasn't correct. And I can see that in this one, I cannot do any moves because I have these barriers here of a P move followed by an O move, or a P action followed by an O action. So when you have this, there's no way you can transpose. So basically, you can move P to the left, O to the right, but you have a PO, it's fixed. So this is incorrect because I cannot transpose it to something that would make sense. And if I go to the higher order example where I had these methods, like again, I have this move here. This is a P move. It can be moved to the left. And I can get this. That is correct because I NQM1, I NQM2, and then I call DQM1 again. But also I can assume that so I have this history where I start by NQ in M1, then M2. And then when I DQ, I actually DQ M2. And basically what happens is that these two moves here are concurrent, and this is an O move, so it can be transposed to the right. And this is something sequential that also is correct. Okay? Okay. And this higher order Q that I showed you before, okay, I won't go through the details, but the behaviors you can get are very complicated. And if you want to write a specification for it, it's very difficult if you want to consider all possible interleavings. But with this criterion, it suffices to consider sequential histories. And in fact, for sequential histories where every move is followed, every O move is followed by P move in the same thread, I can actually write down a specification that, okay, it looks complicated, but I can write it down. So this helps in also writing down specifications. Okay. Why is this correct? So the correctness criteria for linearizability in this case would be approximation, as in the first order case. So we want to say that if L1 linearized to L2, then for every context where I can put L1, the combined thing will terminate, implies that the combined thing for L2 will terminate. And this actually is done compositional. So I use compositionality in game semantics. And the argument, at least at this high level, is quite simple. If we define the semantics so the semantic bracket gives semantics for libraries and contexts. So if you put a library here, it will produce its histories. If you put a context here, it will produce the histories that the context would produce. And then we simply show, well, we have to show that if you link a library into a specific context, L prime K, then the behaviors you get are equivalent if you semantically composed the semantics of the context to the semantics of the library. And now to show that these transpositions you did to get linearizability are correct, well, it suffices to show that, so here you do these transpositions, this PO. If you do a transposition starting from library L, and you have that the library, the context you compose to is actually closed under the dual transposition, then this is enough, because it means that whatever L1 can compose to, for L2 there is in the context something that I can compose and produce the same result. So basically, if we take the dual relation of PO, so the dual relation would be, instead of moving P moves on the left, you would move O moves on the left and P moves on the right. We can actually prove that the semantics for context or for libraries is closed under this dual notion. So therefore, we somehow get this soundness for free. And in fact, this closeness I was talking about, like closed under the dual of this relation, it's exactly the notion of it's exactly the conditions you have in game semantics for concurrent programs, where you prove that your strategies are saturated under this. Well, they need to be saturated under this relation in order to get full abstraction. And this is something that had been done before. It just we applied in this new setting.
Okay. And that proof is done by action using the compositional structure.
Yeah.
The closure property. Well, both, I suppose.
The closure property actually is done. It's a like 5-line argument, because the semantics is done is defined operationally. So you want to say that if I have a P move and then it's followed by another P move, then I can transpose them. And you use simple ideas, like you just look at the semantics and say, okay, well, actually, the two threads, in order for them to synchronize, they will need to access the store. But in these specific moves, I can assume that they first did the access to the store and then the last move happened afterwards. So you can use very simple tricks to show that you can transpose moves. So the hardness then, in this argument, the hardest bit is showing that compositionality. Because you define the model operationally, so composition has to be a theorem rather than a definition. And it becomes actually quite difficult. And we use base simulation techniques to show that compositionality works. Okay, and lastly, there is a special case of this scenario, which is, again came from this paper, which is, well, what happens if the two opponents here, the client and the parameter library, cannot talk to each other? Can I use a stronger criterion? Because if I have an opponent that is weaker, it can observe less things, then maybe I can transpose more of my actions and still be sound. And we can model this as well. We have to break opponent into two opponents, opponent client and opponent library, parameter library. And then we define histories where you have this information in your moves, which opponent is playing, and according to the opponent you play, you also break player to two entities. And then you add another transposition that says, well, you can transpose two actions if they happen in different parts of the game. If one happens in the parameter library and the other in the client. And get this an analogous definition of encapsulation. And again, we can show that this is sound. And we can also show that it proves some other examples that general linearizability cannot prove. Okay, so this is all I wanted to talk about. So this work presents a higher order notion of this correctness criterion called linearizability. We prove that it's sound. We also prove that it's compositional, which I didn't show here. You can also show that you have the criterion itself is compositional with respect to library composition. So if you have two libraries and one linearizes the other, and you compose with a third library, then you can show that then the composites linearize each other as well. The paper is here. What we would like to do further on, this is actually related to Rada's talk, where you can have weaker conditions than linearizability that, for example, can explain or can come from weak memory models. How can we reason about them? And yeah, that's it. Thanks.
Thank you very much. So when you do sort of what you are calling first order linearizability, right? You have a proof technique using linearization points.
Yes.
Here you're not, what will be here linearization points are going to
Yes.
be very hard because you're going to have these holes.
No, there are, okay, so actually, okay, I should have started the talk by saying that we're new in this field, so we hope we don't, I hope I'm not saying anything like ridiculously wrong. But actually, when we were working on proofs of examples, we realized that linearization points are very important. And you can actually locate them, and they happen between opponent call and the response from opponent can be a call or a return again. So you have these points, and we use them in these proofs.
Okay.
Any other questions? Yes.
Yeah, I have two questions. First one is, this seems an awful lot like the conventional notion of vector clocks. Can you differentiate this notion of queues from using vector clocks which have increments in them in the same kind of way?
I'm not sure I understand exactly the questions. You mentioned vector clocks.
Yes. Simple question. How does this differ from conventional vector clocks?
I wouldn't know, but maybe we have discussed afterwards.
Can I try?
Yeah.
So here the time is linear. It's not a distributed system. So it's just a straight line. So the partial orders you see here are interval partial orders. So you don't, so you're sort of in a more restricted time domain. So you're not going to, they don't need vector clocks for this stuff. Yeah.
Which then begs the question, your notion of time, and Hurley and Wing's notion of time was based on a Newtonian background, a constant everywhere, irreversible, smooth background. Is that something which you think is justifiable in this day and age?
Maybe it isn't, but we had to start from somewhere. So we started from like generalizing that word. But
Thank you very much.